That's weird.
No.
I hear somebody say help. Who was that? That's what I need to do. Is go outside and yell, help. Help me, please. Okay, so I got a nice Stephanie, Bree, Emily, Haley. Okay, so let me leave this down here while we're waiting. I'm gonna do a whole lot today, and hardly any of it is any calculus. All right, so I want to just introduce something, and then I think the homework will be fairly easy. We're kind of winding up here. We got a couple more weeks, and then a few days in that third week. How's everybody doing? And I don't know if this is a good day for me to ask this. I haven't looked at the test yet. Okay, so I know some of you had sent me questions, and I tried to answer the questions that you sent me, and I will try to get those back as quickly as I can. Any questions about that or any other comments?
Did we ever get our first test back?
You know, that first test, was the first test or the second? The first test I have the hard copy of. Now I will try to get that back to you before the end of the semester, okay? It's what happened was that I had not figured out all this online technology until after the second test. So if you remember, I sent you a grade. I think I sent you a grade, but I did not actually mark them electronically, which meant that what I did on that first test was I posted a detailed key of the test, okay? So you have that to work with, and I'll try to get it back to you. I was thinking about helping out the U.S. Postal Service and sending it to you snail mail, but I don't know. I don't know if that's a good idea or not. That means I would have to get everybody's Surface Mail address. So on the other hand, the only other way I've got to give it to you is to scan every single page of every single test and send it to you that way. So I don't know which is worse. But I will make sure that I'll try to make sure you get it back. And the thing that I did when I graded them, I couldn't read them when I printed them out. So what I did was I looked at the computer screen. I tried to see what you did wrong, and beside a problem that I could not read, I wrote -2 or -3. So it's even when you get them back, it's gonna be the markings besides stuff I could not read. So you're gonna have to match it up with your other test. That's the test that got caught that just got caught in the whole big transition to then versus now, or whatever. Okay. But good question, Haley. Anybody else? Question? How are things going otherwise? How is it at home? Have you gotten tired of it yet? Yeah, I see Emily.
Yes.
Ready for June.
It's hard to work at home, isn't it? It's like you're out of the school environment and I'm sitting here at a kitchen counter looking at my stove and my microwave, and behind me's whatever's behind me. Fortunately, you can't see what's in front of me because it's my kitchen, which is a big mess. So anyway, Anybody got any concerns or anything you want to talk about at this point? We will try the next test. I'll get this tested back as soon as I can. The next test clearly is not going to have much on it at all because we've really only got 2 weeks and a little piece of a week. I'll talk to you about what I'm going to do about finals on a little later next week when I make a firm decision on that. Finals will also be open note, open book, and I'll talk to you more about that later. So, anybody any questions? Okay, so everybody, I guess let's see what do we got? We got 5 people here, and me. All right, let me share my screen and let's talk to you a little bit. Mostly this is stuff from algebra and pre-calc. So at the home, there's not much homework, so it should be fairly simple. Uh-oh. Okay, let's see what we got here. All right. So what I want to do right now, and I had sort of 2 roads I could go down, and I'm going to go about halfway down each one of them and do sort of the easy parts of what's left instead of just getting real deep into anything here at the end. We did all the stuff in chapter 3 was stuff about what do we do with this derivative thing we've got, and it was looking at functions, increasing, decreasing, all those the kind of things that were on the test. Chapter 4 introduces another function and says, well, what are we going to do with this new function? And this new function turns out to be really important in a lot of different scenarios, which I'll try to sort of give you a general idea of today and just give you a short homework assignment. 4.1 talks about what we call exponential functions. And the kinds of functions we've been looking at in the past are functions where we have x to a power, for example, x squared, or 1 over x cubed is x to the minus 3, or the square root of x is x to the 1/2. In other words, we were looking at things that had a variable for the base here, and the power was just some number, okay? That's just some kind of either a polynomial or a rational function, something like that. And we know how to take the derivatives of those things. There's one new function I want to introduce, and it has to do with looking at a different kind of a function, where what we do is we sort of switch what these were doing. So instead of having x squared, we have the base as a constant and the power as a variable. So we call it, we have 2 to the x, for example. In this one, we might have 3 to the minus x or something like that. All right, so that's when we look at a function like this, it's called an exponential function. All right, and once again, if I have something like this, 1 over 10 to the x, I'm going to rewrite it as 10 to the minus x. All the properties of exponents still hold. I mean, you can bring this up with a negative power, even though that power happens to be an x. So it's a variable power and a constant base. If you've got your calculator with you, I want you to take it out because we're going to use it in a couple minutes. I got mine too. If you look at the definition of what I just said, it says if a is 0 and a is not 1, then the exponential function with base a is given by f of x equal a to the x. Okay, so just raise a constant to a power. Now, the way we're going to graph this, at least for right now, is no different than we sort of in an elementary way graphed things back in high school or in algebra somewhere. We just said, well, we'll pick an x and we'll find out what the y is. So in these functions, you'll have this base is always 2, and this will be some power of 2. So for example, if I say, let's let x be 0. Well, 2 to the 0 is 1. Okay, so that's 1 point right there. Anything to the 0 power is 1, and that's important actually here. So I get the point 0, 1. So I put that on the graph here. I'll put 0, 1 on that graph. If I let x be 1, 2 to the first is 2. So I got the 0.12. If x is 2, 2 squared will be 4. So I got that point right there, just plotting the thing. If I let x be -1, now that's important. You'll get 2 to the -1, but because of the properties of exponents, we know that's 1 over 2 to the first. So anytime you see a negative exponent, you're going to want to drop it down to see what the number is. So there it says -1 is, if I plug in -1, 1 over 2 to the first is just 1/2. So there's the point that goes with that one. The next one, 2 to the -2, is 1/4. So there's that point. I've got them. I didn't plot the thing here because I just sort of wanted to plot it while we were working on it. If I go to -3, and this is important here, 2 to the -3 would be 1 over 2 cubed, and that's 1 over 8. So what you see happening here is that if you get these negative powers, that point gives you a smaller, and plugging in a negative power gives you a smaller and smaller fraction. And in fact, it's a smaller and smaller fraction, but it never gets to 0. For instance, if I put 2 to the -10, would be 1 over 2 to the 10th. And no matter how small that number was, because the denominator is really big, it never gets to 0. So what happens in this picture is that I have something that if I play connect the dots on those points, I have something that looks like that. Okay, so it goes up, down, and it never crosses the x-axis because that thing never gets to be 0. That's an asymptote. Okay, it gets closer and closer to that, but never gets to be 0. You just get a bigger and bigger denominator, which just means you get a smaller and smaller fraction. Okay. If I want to do that on the calculator, I would just grab your calculators if you've got it. I'm gonna take a look at hit your y equal key, because I'm gonna enter this function. Clear whatever's in there. Mine's got a bunch of junk in there, so you'll see what you'll see there. And stop me. I can't get all my screens going so that I can get my calculator on here at the same time. So what you end up with when you do this is we just, again, turn the calculator on, hit y equal, all right? And then you're going to put in, you'll see a y1 screen, and then we're going to put in clear it out. So hit clear if there's anything in there. You'll put in 2, and then you'll, depending on what your calculator does, how new your calculator is, you'll put the up cursor and you put an X. Okay, so my calculator is old, so I'm just going to go 2 to the X, and X is found on this key up on the second column that's got X, T, theta, and N in it. That's all the different variables you could have, but it's going to hit that and it'll get your X for you. Okay. Now, another thing we need to be concerned about is the window. Most calculators, if you hit the window key, which is across the top, most of you have done some of this. If you hit the window key, you're going to set the size of your screen. A lot of them are set -10 to 10, -10 to 10. So you have X min, X max, the scale is 1, X min, Y max, the scale is 1, and you can do that. I didn't go very far on this one, and so what I think I'm going to do is I'm going to let it go from I'm going to let X min be -3, and remember, hit the minus sign, not the subtraction sign. So I'm going to let that be -3, and I'm going to go to 3 on the X coordinate, and then I think I'll just leave the Y min and the Y max the same. All right, once I get that in there, when I hit graph, all right, let me see. I forgot to put in my X. That's important. When I hit graph, I see what I should see is this thing that's sort of shaped like this. Okay, it's just called, it's an exponential curve. Okay, now, what you've been hearing a lot about in the news lately, you're only hearing about the coronavirus because you can't escape it. And they talk about exponential curves and the virus growing exponentially. Notice what happened when I put in positive powers of these. I got 1, 2, 4. If I put in 2 cubed, I'd get 8. 2 to the 4th would be 16. Things are doubling. So, you know, you get one person sick out there, that person makes 2 people sick. Those people make other 2 people each sick, and then and things get out of hand fast, okay? That's what we're talking about when we talk about an exponential growth. Now, what they're talking about when they're talking about flattening the curve is going away from a curve like this. There are other curves that say, well, maybe we can flatten out what's happening so that we don't completely overwhelm the medical system, basically, is what's going on there. Lots of people are getting it. If you go way up to these peaks, which unfortunately the United States has been doing, you get scenarios like happened in the city, in New York City, where you get your hospitals are just turning everything into a coronavirus room, and they've got people in the halls and everywhere. So that's why we're doing all this social distancing, and should be doing more testing, so forth. But anyway, an exponential curve just keeps going up. That's not what you want, okay? So that's called something called a logistic curve. If we have time, we may talk about that too. But that's what we talk about when we talk about an exponential function. So let's look at one more. Anybody got any questions about that? It's just plot the points, put it in your calculator, just look at what it's looking like. If I look at this next one, and the only difference in this next one is I got 3 to the minus x. So when I plug in 0, it's still 3 to the 0, so it still goes through 0, 1. So 0, 1 is a pretty important point for these. At time 0, there's one thing out here, one case of the coronavirus, and then whatever happens. But this case, if I put in 1, it's going to be 3 to the minus 1. And 3 to the minus 1 is 1/3. So over here, where I have 1, I'm going to get a point that's 1/3. So it's pretty close down there to the axis. If I put in 2, the minus is there, so it's 3 to the minus 2. That's 1/3 squared, or 1/9. So it's getting closer and closer to that axis with those points. On the other hand, if I put in -1, minus a -1 will be 3 to the 1st. So I get -1/3. If I put in -2, minus a -2, so 3 minus a -2 would be 3 squared, and that would be 9. So what you see in this case, when there's a negative power of x on that thing, or negative x on it, the graph looks like that. So that's what that looks like. So it can be either going up, if this is just an x, or it can be going down. And it also gets closer and closer to that. Now, in general, let's just talk about both of these things. Let's see sort of the properties, because we know a lot about properties of graphs now. Question about any of that, about graphing those two. In this one, in the calculator, you put in 3, and you put minus x, and you'd see that. You'd see that happening. If you put it, we've used the table a little bit in here. If you put that function in and make a table, hit the table, you could put in these values and it would compute those values for you, okay? They wouldn't be very nice because they'd probably be in decimals, but that's what's gonna happen. So here's what, in general, we're looking at. We've got this a to the x thing. And if it's a to the x, and x is just not a negative, not a minus x, but just an x, your graph looks like this. And how steeply it grows depends on how big a is. I mean, clearly if you raise 2's to x powers, you're not going to get something as steep as if you raise 3's. The 3's will go up faster and they'll also diminish faster. But what we see about this, number one, in both of these, this one is the one that had the minus x, it comes down. They both get closer and closer to the x-axis. So y equals 0 is a horizontal asymptote. So they both get closer, that one going in one direction and one going in the other. Their domain, I can plug in any x I want, guys. It's not going to make a denominator 0, and it's not going to give you a radical, a negative under an even radical. So the domain on these exponential functions is minus infinity to infinity. Now, if you look at this shape, and I do this with my cursor, increasing or decreasing on that one? Cursor's going up. What's it doing?
Increasing.
It's increasing. Is it concave up or concave down? Does it hold water or does it dump water?
Concave
Cold
up.
water.
Yeah, it holds water. It's concave up. So this one's increasing concave up. This one is decreasing, but it's also concave up. Okay, so it holds water, but it's coming down. So we know sort of these are like two of our basic shapes when we were looking at this stuff. The range, guys, I recall that the range is what the y's can be, the possible values of y. That's what we mean by range. And my pen's doing bad things today. Possible values of y. We kind of talked about that here, guys. We said it doesn't ever go below the axis here. It could go below the axis if we took a negative this and it flipped it down there. But in this general form, the range goes from 0 to infinity. And it never crosses 0. That's why I put a parenthesis there. So both of them, and it goes up infinitely in that direction on both of them. So you can get any y, but it's always positive. Okay, it's always positive. And that's the range. Okay, question about that? One more thing that I just said that if we did have something like this, f of x equal minus 1 times 2 to the x. Well, if you look at, we looked at 2 to the x a minute ago, it looked like that. So that was just y equal 1 times 2 to the x. If you multiply it by minus 1, it's going to make all those positive y's negative, and it'll be this picture, but it'll flip it down there because everything that was positive up here is going to be negative because of that negative sign. So if you were to plug points into this, you'd see it going down there. But notice now, instead of going through 0, 1, like this one did, if I plugged in 0 here, it would be 2 to the 0 would be 1, it would be minus 1. So it goes through 0, minus 1. So in other words, everything gets flipped because of that minus sign right there. So you might see something like that. Okay. So I'm just gonna hit the highlights on this stuff. Part of your homework is just take some of these and graph them on your calculator, or try to graph them a few by hand. So let's talk about how you see exponential functions in applications all the time. If your business is doing really well, maybe your profits are growing exponentially. One person buys something, they go out and tell somebody it's a great store, they come in and buy something, 3 more people come in and buy something. Eventually it tapers off, but it's got that kind of big growth initially. So if I look at this one, it says sales in billions for Walgreens from 2000 to 2010 can be modeled by this function right here. Now, guys, that's an exponential function. It's got a funky kind of coefficient on it here, but it's still a constant raised to a power there. And what it's saying is we can estimate the billions of dollars worth of sales that Walgreens has, and I'm sure it's billions of dollars because pharmaceuticals are big money, by this. And they're going to say, well, we're interested in the years from 2000 to 2010. So T, and they're going to let T equal 0 correspond to the year 2000. So for example, if I said to you, I would like to know what they're making in the year 2000, you would take T equals 0 and plug it in right there. That would make it easy because anything to the 0 power is just 1. And what I would get, so in other words, S, the sales in the year 2000, or S of 0, is 22.52. Because that's 1. Again, anything to the 0 is 1, and you just get 22.52 times that thing. So $22.52 billion in 2000. Okay, so I just plug it in like I normally would. You can use your calculator on this one. Let's just see, just make sure we're using the calculator properly. It then says, oh, you know what? I did something not good here. I said that this was a model that was good for 2000 to 2010. And I asked you to predict the sales for 2018. Yeah, that's a little suspicious because they didn't tell me it was that good a model. Maybe it doesn't keep rising that far, but I'll do it anyway. I'll say, what if this model's good until 2020? Then I'll put in for 2018, I'll put in 18 because 2000 is 0, so 2018 is going to be 18. I'll raise that to the 18th power, so it's going to be, you might want to try this on the calculator and check me out here, 22.52 times 1.125 to the 18th power, and what I got was 187.63 billion. Let's see, I'm going to let you check that.
That's what I got too.
Okay, great. Okay, great. So that's, is everybody okay? I'll just put in, I'll put in that, I'll put in times, I'll put in this number, and then I'll go up 18. If you got a newer calculator, when you put that up key, it gives you a tiny little box where you put your exponent in, and then you cursor back to the right, and it'll put it down, and then hit enter. You're probably used to using that. Mine's still old, still leaves the cursor in it. Okay, question about that. All right, let's look at another one. This is another similar example. And this is one that pops up a lot in business. It says, suppose the annual rate of inflation is 10%. We've been having really low inflation lately. All right, but I guess it was back in the 90s. There was a lot of inflation going around. But it says the cost of goods over the next 10 years. Suppose the annual rate of inflation is that, then the cost of goods over the next 10 years, the approximate cost, we'll say, I should have put that in parentheses, the approximate cost of services and goods during the next 10 years is given by C of T, that's cost, and T is time, is P times 1.10 to the T, where P is the present cost. So let's suppose, and I didn't compute this one, let's suppose that the cost of a haircut is $25. That was a Freudian slip right there. $25 is cheap for a haircut if somebody else is doing it. When I was in that cast, I was going nuts to have my hair washed. And like, it cost me $30 just to have my hair washed. I'm like, good God, I need to get out of this cast fast. And I'd have my long hair cut about twice a year. So anyway, so we'll say that, I'm putting now is what I meant there. Suppose the cost of a haircut is $25 now. How much will it cost after 5 years? Well, what this model says is if that's the present cost, if 25 is the present cost and inflation is 10%, then this exponential function will give you the cost after 5 years. All right, so what I did was I put in a 5-year, and I'm going to let you do this too while I'm doing it. It's going to be 25 times, put the parenthesis over 1.10, and then close your parenthesis, get your cursor up, raise it to the 5th power. I got 40.26. That look like what you got? You got your calculator?
Yeah, I got that also.
I got that too.
All right, so a little over $40. That's sort of like more what it's like today, okay? Actually, you can't really get it done for less than 50 unless you got a friend. All right, so anyway, does everybody see what I'm doing with that example? Okay. Now, what you can do at this point, there's some problems in here just like the ones I've done. I have not actually typed out an assignment sheet yet, guys, so just take a minute to write that down. I don't know, hopefully I worked from 9 o'clock until like 10:30 yesterday, and I managed to get most everything done, but not all of it. So I didn't get y'all's assignment sheet done, and I'm not sure exactly where I'm going, so that's okay. But this is some of the things to graph. You can graph them on your calculator, and it's some of these problems that look like these applications problems. They're really just plugging things in. Okay. So that's in 4.1, and I've skipped a few things in there, but this is the basic stuff from there. Look at it, see what you think, and we'll come back and talk about it if you have any questions. All right, the next thing I want to talk about is I'll leave that up there for a minute, is something called the natural exponential function. Now, I need to talk about this number E. E is a very famous irrational number. Second only to pi. And you guys are probably more familiar with pi than you are with E, but pi, you know, 3.14, blah, blah, blah. And then it's irrational because you can't predict what's going on with the numbers. E is another irrational number. Its value is 2.71828182846 ... It makes you think it's going to give you a pattern here, but it doesn't. It goes away from that pattern right there, that 1828, 1828. I had and this is this crazy things you remember that your math teachers tell you and you think, why in the world did they even tell me that? But I remembered it after just forever. I don't know why, but I had a math teacher that said, oh, it's 2.71. And you can remember that 1828, 1828, because that was Andrew Jackson's second term in office. And I'm like, oh my God, what am I supposed to remember about Andrew Jackson's second term in office? But to this day, I know when Andrew Jackson's second term in office was, for whatever that's worth, which is not much unless I'm on Jeopardy and they ask me something like that, okay? But that's what E is. Now, let me show you how to get it up on your calculator, and then I'll show you what we're essentially gonna do with it. A little bit about what we're gonna do with it today. What you're gonna do on your calculator is hit your second key, which is the yellow key on mine, at least, on the almost to the top of the first row. So you're going to hit that second key, which sort of gives you an arrow. And then you're going to hit the key that says LN. And LN is down that first row. You'll see it. It's right under LOG. It's LOG and then LN. So hit that LN. If you'll look over the LN, you'll see a little teeny e to the x, okay? If I want to find out what the value of E is, I'm just going to put in 1 there. So you'll see, here's what you see. It looks like, it'll give you this thing right here, and then it'll ask you to put something in there. So if I put in 1 there, and then close the parenthesis, and hit enter, you will see all those digits I put in there. Actually, your calculator only holds about that many of them, so it stops at the 1828. So that gives you what e to the first power is, and that's a famous irrational number. Now, so if I wanted to find e squared, because I kind of want to graph this thing, if I want to find e squared, again I'd hit second ln, and then I'd put in a 2. Close the parentheses and enter it, and I got 7.389. So it's approximately that. But irrational numbers have to be cut off somewhere. But there's what e squared is. So e to the first is that. E squared is that. I'm going to do one more, guys. Let's say we want to do e to the -1. So second ln, and then we're going to put in -1, enter. I got 0.368 if I round it, about 0.368. Oops, 8. All right. So this function that we want to talk about is called the natural exponential function. Now you think, well, it's anything but natural, because this e's a little strange here. It's this irrational number. It turns up that it pops up in a lot of applications, and you'll see one of those later in the week. So if I have this function, f of x equal e to the x, it's still just a number raised to a power. It's just that this e right here has is just a special number. Instead of 2 to the x, it's e to the x. All right. If you make a table of values for it, and start plugging in things, notice that if you let x be 0, e to the 0 would be 1. So just like those other exponential functions, it goes through 0, 1. It doesn't matter what I raise to the 0 power, it's going to be 1. If I use some of those other values I got, e to the first was 2.71. I just cut it off. I know it's 8281828. It's about 2.7. So at the point at 1, I plotted 2.71. At -1, we just found that one. I actually rounded it to another place when I put it on the graph. It was -1.37. And when I go back, and that's -1 right there on the graph, that was 1, I would get 0.37. Now, if you do this enough, if you were to put a square in, if we would put a 2 in there, did we do that a minute ago? We already do e squared. I think we did. But yeah, we did 7.389. All right, so that's 7.389. What you can see is if I'm putting in 1, 2, 3, 4, I'm raising a number that's bigger than 1 to a power. It's getting bigger and bigger. But if I make the powers negative, for instance, if I put in e to the -2, do that. Okay, second ln, and I put in -2, I get 0.135. Well, that's getting even smaller than it was at -1. So at -2, it's 0.135. So it behaves exactly the same way that the other exponential functions behave. Its domain is all real numbers. I can put e to anything I want. This one happens to increase. If it had been a -x, it would have decreased down here. It's concave up. The decreasing would have been decreasing concave up there. It has the same shape as other exponentials. Now, this is a weird definition to give at this point, but we're going to see some benefit in it a little later. I said I wasn't going to do much calculus, but I am going to talk about a limit here, and I'm going to want you to do something on the calculator for me here. It says the limit of this function is e. Now, that's a weird looking function right there. It says as x gets closer and closer to 0, this number gets closer and closer to e. What you can do, and I'll let you do it, try this tonight, if you look at the function f of x equal 1 plus x to the power 1 over x. Now, this is exactly the way you need to put it in your calculator, guys. Lots of parentheses. 1 plus x to the 1 over x. And it's going to give you a graph. And if you want to find out, just look and see what the limit is. And we'll look at this. We'll look at this tomorrow. That's a cursor, by the way, there, guys. That's making the power go up. Okay. If you found out whatever the graph of this thing is, as you get closer and closer to 0, in other words, as you go this way in the graph, you will see it getting closer to this number, 2.71 da 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 da. And again, that's pretty important, but it is a weird looking function. What you're going to do there, guys, is use your tracer on your graph. Just put this function in and make your tracer get closer and closer to 0. All right, and what I mean by hit the trace key. So use.
Is that f prime of x?
No, it's f of x. That my f looks bad. That's a good question because it's not f prime. It's f of x. Okay, it's just a f. Better. Thank you. So hit the trace key there. Hit the trace key, and you'll be able to see that it does get closer and closer to 2.71. That turns out to have big implications in business right there, and we'll talk about why that is a little later. Okay, so guys, I had a little more, but you know what? I'm going to call it quits for today. I don't want to start it. Let me take a break. The homework that you saw above is that we did when we were right there, is just the first stuff that I've talked about. It's just in section 4.1. Shouldn't be too hard. We'll come back and we'll pick this up again tomorrow. Anybody have any questions? Okay. I will be grading the test. I'll get them back to you as I grade them. It'll probably take me a couple of days to get everything in and graded. Please email me if you have any questions about anything, and we'll talk again tomorrow. See you later.
All right,
Go have
thank you.
Bye. Have a good day.
Thanks. Bye-bye.
Okay.